anything with commercial relevance where operating flexibility, that is range, payload, airports that you can fly to and from anywhere, and the economics, anywhere that matters and you need to get to scale, hybrid electric is what'll get you there. Everything else is fundamentally limited either from the technology, infrastructure, market applicability, or safety and regulation sides. And hybrid threads the needle perfectly right now. And everything else you have to place a bet on an unknown that's completely out of your control, whether it's battery energy density or hydrogen costs or infrastructure. And hybrid doesn't place any uncontrollable bets. It's just about good execution.
Welcome to The Vertical Space, the podcast at the intersection of technology and flight, featuring deep dives with innovators, early adopters, and industry leaders. We are your hosts, Jim Barry from Celerity 05 and Peter Shannon and Luka Tomjanovic from Radius Capital. At Celerity 05, we believe that breakthrough air transportation capabilities come from leveraging current and emerging technologies, and that companies achieve profitability through relevant technologies, strong teams, and a deep understanding of the aviation market. Connect with global aviation experts at celerity05.com for feedback and recommendations to chart your path to success. At Radius Capital, we invest in early-stage deep tech that redefines what is possible in aerospace. We partner with founders building next-generation aerospace capabilities, from advanced design and development tools to the digital transformation of the flight environment, novel use cases and forms of flight, and the software and systems that make them possible. If this describes you, reach out. We're excited to connect. All right, let's dive in.
Hey, welcome back to The Vertical Space and our conversation with Kevin Nordker, co-founder and CEO of Ampere. For those of you who've been listening to many of our last several podcast discussions, especially those with Rob Britton and Jeff Luckett, you'll find our discussion with Kevin a perfect follow-on. After discussing areas where some may disagree with Kevin, we launch into an overview of electric aviation and the industry that blossomed due to its introduction. Kevin also discusses that the electric-only industry hasn't seen the battery progress that many had hoped, which has pushed back the timelines of many fully dedicated electric vehicles. We also discuss how electric-only vehicles, especially eVTOL, have more limited near-term use cases. We then talk about hybrid propulsion versus electric propulsion. We discuss what parts of hybrid propulsion are changing the fastest today and its different and unique use cases. We then discuss why an operator in regional air mobility would select an electric vehicle versus what some would consider the more obvious choice of hybrid electric propulsion. We delve a bit deeper into regional air mobility and how overall electrification may increase the use of regional air mobility. We discuss the pluses and minuses of pure electrification, hybrid, and traditional aircraft on regional air mobility as well. Kevin wraps up our discussion with some great advice for our innovators and entrepreneurs. Kevin, thanks for joining us for a terrific discussion. And to our guests, we hope you enjoy our talk with Kevin Nordker as you profitably innovate in the vertical space.
This episode of the Vertical Space podcast is brought to you by UAvionics. UAvionics is the leader in low size, weight, and power certified avionics for manned, unmanned, and advanced air mobility aircraft. Let UAvionics help you achieve your goals, whether that be type certification, airspace access, or beyond visual line of sight operations. UAvionics has certified and certifiable communications, navigation, and surveillance avionics for your aircraft. So head over to uavionics.com or Google it to see how you can start flying safer and move your platform forward into shared airspace.
Kevin Nordker is co-founder and CEO of Ampere. Over the past 8 years, Kevin and his team have pioneered practical, compelling electrified flight through the upgrade of existing aircraft types. In 2019, they flew the world's largest hybrid electric aircraft. In 2020 and 2021, they deployed and demonstrated electrified flight with multiple airlines across the globe. With over 23,000 miles flown hybrid and 12-plus regulatory flight approvals across 3 countries to date, they're a leader in hybrid electric aviation. Prior to Ampere, Kevin contributed engineering and program management expertise to advanced aircraft and satellite technology development programs at Northrop Grumman and as a research fellow at Caltech and NASA's Jet Propulsion Laboratory. An entrepreneur at heart, Kevin is driven to apply the science and engineering disciplines of large aerospace organizations to pressing environmental problems here on Earth.
Hey, Kevin, welcome. Great to have you on the show.
That's wonderful to be here. Thanks.
So if we start by asking if there's anything that very few in the industry agree with you on.
Yeah, I like this question a lot. And I was thinking through, there are about four things, I think, distilling down what differentiate how I'm thinking about this industry, not from everybody, but probably aren't the party line in general. The first is we're in sustainable aviation, and there's a lot of talk about new design planes and new markets, eVTOL and high speed new design jets. And first is I believe that we need to start with propulsion rather than airframe design. And there's a whole lot of good that you can do with new airframe designs, but novel propulsion is how we've seen these transformative moments progress in the past, whether that's the dawn of powered flight or the jet age. And I think you need to get the propulsion right before you start doing the transformative vehicle designs. There'll be a lot of people out there that might disagree with me on that one. Number two is that,
Kevin, if I could jump
yeah,
in. I had a very senior transportation leader call me last week and say exactly that.
that's great.
After listening to so many of our podcasts, he called me up and said, I want to talk about propulsion.
Yeah,
And then as we were preparing for this, I was thinking, oh, wow, this is perfect timing. So at least there's one person out there who agrees with you.
I appreciate that. He and I should grab coffee sometime. I'm sure we'll have plenty to talk about.
Great. And just to add, this strikes me as perhaps more commonly held view than perhaps you are alluding to. All the new technology waves in aviation revolve around or are enabled by new propulsion. So, what is it about this particular statement that the industry disagrees with you on?
It's the idea that you need to do the new airframe design with the new propulsion in the first embodiment. Ampere, over the years, has gotten a lot of pushback from industry stakeholders about doing upgrades of existing aircraft types, that you can't capture the full opportunity, they say, by upgrading existing plane. You really need distributed electric propulsion, or you need the new airflow augmentation or your vertical lift features, and that they believe that those features are going to drive the adoption dynamic, and that propulsion retrofits, which is the path Ampere has taken, is not a sufficient starting place. I think that's where the differentiation comes in, because certainly eVTOL, let's take as an example, requires novel propulsion. What I'm saying is we can decouple those as a first step, not to belittle the benefits that you would get from a clean sheet design, or maybe it's ultra short takeoff and landing performance, but the fact that designing a plane around propulsion that is not yet certified, that does not yet exist, is a recipe for having to redesign that plane half a dozen times. And we've already seen people burn a lot of capital going through that path this turn of the wheel. But if you just look in history, I mean, this is new design planes that didn't do it around existing propulsion. That's one of the big gotchas in the design space.
And there was another thing that you wanted to flag.
This is going one layer down there for propulsion. Hybrid electric is the only approach that makes sense right now. There are many exciting technologies. Obviously, fully electric is a dream many of us have. There's some corner cases where fully electric might work. There are a lot of people pushing hydrogen, but the reality is just like on the ground. Hybrid electric is going to lead, it is the gateway technology to this future. And I think it's going to be the gateway technology for decades.
I didn't expect a different answer from you.
I'm talking about anything with commercial relevance where operating flexibility, that is range, payload, airports that you can fly to and from, anywhere, and the economics, anywhere that matters, and you need to get to scale, hybrid electric is what'll get you there. Everything else is fundamentally limited either from the technology, infrastructure, market applicability, or safety and regulation sides. And hybrid threads the needle perfectly right now. And everything else, you have to place a bet on an unknown that's completely out of your control, whether it's battery energy density or hydrogen costs or infrastructure. And hybrid doesn't place any uncontrollable bets. It's just about good execution.
Kevin, elaborate on this point a little bit. Why is it that the industry doesn't think that hybrid is the way to go?
I think back to when we founded Ampere. And I think back to a lot of the people in this industry who have such deep passion for making a positive impact on the world around us. And those core motivations for many are about usually one of two things. Either they care deeply about the environment and they want a true zero emissions solution. And that forces their designs into a fully electric or a strong hybrid where you're flying fully electric for some period of time, or a hydrogen where they can claim a zero carbon emissions in flight. It's a fuel cell. And so what you see is this desire to have a pure carbon remedy. And that causes people to not prefer the hybrid electric type approaches or these hybrid approaches where 50% fuel savings, 50 to 70% in our vehicles is phenomenal, but it's not zero. And if you're here on only principle and unwilling to look at anything but the pure solution, then that would bias you against it. The second is there are some people who are pushing toward this idea of you have to start with the absolute simplest possible architecture, even if it's not possible today. And electric is phenomenally simple. And the maintenance costs are super low. And in theory, you can get the economics to play out depending on your battery assumptions. And if you have certain optimisms in that area, then you don't want to give yourself the complexity or the crutch of having to do the partial via hybrid solution. And I think that keeps some people away from it because they say, oh, batteries will get there. Like, let's just wait around for those. But I think they miss the point that if you can serve 10 times the market size by using hybrid electric and you're saving half the fuel burn on that, let's do the math. It's 5 times the positive impact of if you were zero emissions on that 1/10 of the market.
Let's talk about electric aviation, zoom out a little bit. Catch us up on some of the major milestones in electric aviation over the last several years.
So electric aviation has had some pretty amazing progress in the last decade or so. The earliest companies in this industry were founded in the 2010s, but very few were talking about them at that point in time. You had the starting of the NASA X-57 program. By the time Ampere was founded in 2016, there still really weren't that many companies that were publicly acknowledged doing work in this space. Since then, we've seen this blossoming of ideas, of concepts. I remember the first time, I think, Peter, you might have even been there at the Uber Elevate conference out in Dallas in 2017. There's this industry that built up around the enthusiasm for electrification. And then you saw hundreds, I believe the number peaked at over 700 different projects in this space. A lot of ideas, a lot of people who really get excited about designing airplanes and want to go through the features. So big milestones. You've had first flights, whether those are the flights of the Pipistrel Alpha Electro or ultimately that being delivered to customers around the world. You have the first flights of various development program aircraft, Ampere's first flight in 2019 and subsequent iterations, for example, our Caravan flight in 2022. The industry's also made progress from simple demonstration of flight capability to very specific capabilities. So in eVTOL, the progress of transitioning from vertical lift to fixed wing flight has been a big challenge where still only a handful of companies have safely made that transition or done so with a pilot on board. These are critical milestones that will drive confidence in adoption and ability to getting regulatory approvals on the operations. You've seen some incremental progress along the battery energy density standpoint. So a lot of folks are waiting for batteries to have significantly higher watt hours per kilogram. So the gravimetric energy density in the lithium ion batteries in particular. And we've seen some modest progress on that and some really amazing announcements. Some groups who are in the chemistry side trying to get up toward past 500 watt hours per kilogram, targeting 1,000 watt hours per kilogram, and pretty audacious goals. I think the industry hasn't yet seen as significant of progress as many had hoped, and that's pushing back timelines for entry into service of the fully electric vehicles. And then from a certification standpoint, some pretty big milestones back to 2018, where we were part of kicking off a ASTM committee around electric vehicle chargers, through all the SAE committees or other industry groups working together on certification. While these might not be the visible milestones that hit the press, they're certainly the milestones in progress that help move the industry forward. And so watching folks get their first certification bases established or get means of compliance agreed upon or special conditions moving forward, ultimately looking, I think here in the next few years, we'll get the first full regulatory approvals for commercial operation. And each of those are some of the very meaningful milestones that are happening real time and coming up soon.
One of the surprises for me was the lack of certification events following Pipistrel's EASA certification of their Velis Electra aircraft in the LSA category that was back in the summer of 2020. And then earlier this year, I think in March, the FAA issued an LSA airworthiness exemption for that same aircraft. But here we are 4 years later, and no other electric aircraft has been certified. Why do you think that's the case? What's the bottleneck?
Yeah, I think there are a few things. One is the regulatory basis for certification, and the Pipistrel products didn't fully open up the Part 23 or the vertical lift certification arena. It was in a different category initially. And I think that while it made progress, and maybe others could have taken their products through that same, the identical regulatory pathway, many of the products that are out there that we most are paying attention to are in Part 23 or the vertical lift category, which was not as fully opened up through the Pipistrel application. I think second was a bit of the dynamics in the market. So with the pandemic in 2020, I think a lot of milestones were dragged out a bit. 2021, money was easy, and I think that meant that money went to moonshots. So easy money doesn't mean it goes to practical near-term wins. And so I think that a lot of the money that was being invested in late 2020 and throughout 2021 was going toward long horizon plays. So purposefully not aiming at super near-term strategies. And I think that overfunded those, and we've seen many get significant funding, but then burning through it. And I think it underfunded the pragmatic strategies. And so what you saw was further pressures on or delays to the timelines for entry into service for those that might not have been as flashy, but were just making the next increment of meaningful progress. And then we've seen the retrenchment of the markets where now there's a bit of a recoil. I think the industry's at risk of losing credibility, given all the claims that were made and failed to be lived up to, whether that's certain timelines or product performance or cost metrics for the products. And so I think the industry, in particular, the capital allocators, may be licking their wounds from those moonshot projects that didn't play out, which doesn't help, again, those that are near term. What it does is it pulls back more capital away from everything. And so if you're looking at that as a lowering tide, each of these dynamics, I think, has pressed away from certification milestones that we might have otherwise hoped to see more rapidly after the Pipistrel's early successes.
And what about the maturity of the enabling technologies themselves and the certifiability of the motors and batteries? What's the status there? And I was recently catching up with another founder, and we started talking about this, and it was surprising to hear how the regulatory bodies are trying to apply traditional propulsion system requirements to electric motors. So, for instance, I think there's a requirement somewhere in internal combustion engines that they need to be able to run for, I think it's 5 minutes in max rated power, whereas an electric motor reaches its thermal limit a lot quicker, maybe within 2 minutes or so before needing to throttle back. And so that is one contentious issue, allegedly, as is the example of having dual magnetos in ICE engines. And does that translate into double architecture in electric motors, all of that increasing mass, increasing budget, and really not making that cost equation as favorable as initially expected. Do you have any insights into those aspects of how the bottlenecks are being tackled at the certifiability and the maturity of the technologies?
I think that this gets to one of the really critical and core risks in the industry, which is the supply chain and the ability to not just invent something, but to produce it reliably many times at a good economics. That's really what builds the markets here. I think the regulatory bodies are trying to adapt to what they know. And those adaptations, whether it's the Part 23 rewrite, which adapted combustion type expectations to an opener, larger net for what kind of technologies could actually be used to meet those requirements. But in the details, they're still looking for that familiarity. So, what's your mean time between failure? How long can you run at full power? What are the failure modes and effects? And making sure that you're going through the detail on that. This is the specifics that you get into when putting together your program certification plan, your means of compliance, or ultimately going through the testing for your type certificate or STC. And it's really where the rubber hits the road in the industry. I don't think that all the answers are there yet. I think there are the early entrants. Certainly, Ampere is, at least to our knowledge, the only company working on a hybrid electric propulsion system certification program actively with the FAA. And so this means that we're clearing many of those open questions actively with them and collaboratively with them. It also means that we have expectations upon our supply chain that merge over time if something, for example, with the FAA brings up or highlights a requirement that we did not expect. As you talked about with the motors, or there's these questions about redundancy, there's what you could expect as a technologist. Like, you'd understand the technology and you believe this to be true, some level of safety, let's say. But that does not mean that will be accepted on the first pass through certification. And in fact, I think that the first paths through certification are going to be relatively risk averse and risk managed in those setting a higher bar for redundancy, not giving you credit for levels of safety that you think you might deserve. So, case in point, for the lithium ion batteries, no matter what you do to the cells, no matter how you package those cells into your modules, no matter what physical interconnect or disconnect controls you have that might mitigate thermal runaway, or physical barriers that might mitigate propagation, or software layers that are on top of all of that, the belts and suspenders and layers of safety, at the end of the day, the FAA, probably rightly so at this stage, requires you to show that you have physical barriers that if you force the battery into thermal runaway, the vehicle will be safe. So you don't get actual credit for everything below that. You need ultimate safety and then all the other stuff that you thought was going to be sufficient. And these are, again, I don't think it should be surprising to anybody that the earliest applications we're going to take the most risk managed approach. But what it means is that when you're a battery engineer on your fully electric vehicle, you're now doubling the weight of all these additional systems when you thought you could get there just with a really good BMS algorithm. And so what it drives is the decisions, and it drives ultimately the designs into corners that might not be viable given some of those early assumptions. This is why we pushed again toward hybrid electric, because with a battery pack a third the size of a Tesla pack and able to take on the extra weight and the payload hit along with it for all these physical layers of safety, we still have phenomenal performance on our system. And I think that these are areas where the industry is trying to navigate alongside the regulations to mature the solutions and the risk together.
Kevin, what electric aircraft are selling in meaningful numbers today that you're impressed by?
When you say selling, I'm going to assume you mean where there's a cash transaction and somebody ends up with an airplane in their hangar at the end of it. And right now, the only airplanes that are selling are the Pipistrel aircraft at this time. There are many organizations placing pre-orders for eventual deliveries. but at this stage, very minimal on the actual sales in this market.
So, Kevin, what are you seeing as the FAA's thought process for how industry is going to incorporate improvements in hybrid electric propulsion systems into these aircraft in the coming years? These aircraft are long-lived assets. Batteries still seem to be improving pretty markedly over the years, motor technology as well. So if you certify something, on the one hand, you're locked in at that point in time. Are they going to use an STC method for bringing improvements in, or is there something that is even more fluid for allowing that they have in mind?
It's a really good point because the technology base is moving so much faster than the time scale of a vehicle life, right? These aircraft last 40 years and the batteries are improving on the order of every 2 to 3 years. You'd expect people wanting an upgrade of their battery pack to the next generation, a little bit like people might want their new iPhone every few years. The way you go about certifying your product matters. And if you wrap everything into the type certificate, then you need to amend or update the type certificate when anything changes. And so that would require a supplemental type certificate for certain types of changes. Generally, propulsion systems, propellers, or airframe changes require a new type certificate or a amendment or a STC, supplemental type certificate. There are things you can change on an airplane without having to go get an STC. You could replace a conforming part with an equivalent part. You're able to show certain equivalent levels of safety. And so there are efforts to try to find ways that these components, which would be replaced over time, let's use the batteries as an example. Batteries degrade over the cycles of use, and every few years you want to replace those. Do you have to go get an STC for the new battery pack? Are you able to use a TSO type process, basically a lighter version of those approvals? And it really depends on exactly how that battery pack was incorporated into the vehicle level certification. So is it part of the engine? Is it part of the aircraft? Is it a safety of flight critical component? And then as technology improves, one of the things in aviation is you lock yourself into the part that you designed, and that in any change in that part requires a change in your regulatory approval. So as batteries improve, how do you go through that certification pathway? Again, generally what I think the industry will see is we guarantee equivalent performance while providing improved performance. And that all you're doing when you're meeting the existing regulatory waterline is you're saying we're at least as good as we were previously, and we haven't changed any flight characteristics. The question will be, when do you want to take credit for that? When do you want to allow the operator to plan a longer route? You can give them more energy, which gives them more safety, or maybe it gives them more flexibility on how many flight miles they can perform or when they need to recharge at the other end. But it might not be part of the underlying certification performance capability of the vehicle that you've sought from the regulatory body. Now, this is a nuance, but it's the difference between having to go through the full cert program for the new tech or just increasing performance, but taking credit for an equivalent level of safety. One specific point here in our hybrid system, I have triplicate redundancy in our hybrids. We are phenomenally safe, and I believe safer than a traditional combustion engine would be, where it's a single point failure for the traditional engine. And in Ampaire's system, we have redundancy, 2 layers of redundancy in the combustion engine, and then also this independent electric system, which is able to carry you further as well. But am I going to get credit for anything more than a single engine capability? Probably not. And that's understandable, at least initially. And I think over time, what you'll get is additional credit for those things from the regulatory body. And in the interim, when new tech motors or batteries come out, it'll be at equivalent levels of safety as what was there previously.
What components of the hybrid electric propulsion system are changing the fastest right now? Be it the battery systems, the motors themselves, power electronics, or something else. What do you see as the fastest changing or evolving
Yeah, I mean, the fastest changing components historically have been those which had the benefit of riding the coattails of other industries. Aviation, as big as we love it and believe it is much smaller than as a market driver than other forms of ground transportation. And so we have been the recipients of rapid technology improvement across lithium ion batteries as energy density, volume density, and cost get brought down. The motors have been a truly the underlying enabling factor in many of these cases. So the power density of motors is pretty phenomenal compared to where it was a decade ago. And we still see companies that are, and we work closely with companies that are pioneering in this space. And you're getting great efficiencies and really high power density out of these motors, where certainly Ampere has locked most of the components for our launch product. But we have a flying test bed where we're able to bring in new technologies, where we first flew a silicon carbide inverter, when we have brought in new motors, inverter, and energy storage tech. And it's really in the motors and batteries that most people are pushing firmly for innovation, and then a bit in the efficiency of the power electronics. But a lot of that currently seems like it's lab scale technology. And while our work with ARPA-E and NASA enables us to make that move even faster, I hesitate to think that lab technology today is going to rapidly enter commercialization anytime soon. I think we've seen a consistent trend that timelines for those developments take much longer than the technology teams would have originally anticipated.
Is aviation going to continue to benefit from advances in the automotive industry around the batteries that they use, or is there going to be a fork in the road where the needs of aviation diverge from what the auto industry is pushing towards?
Yeah, I think the auto industry used to have range anxiety, but then battery energy density got to the point that you can drive hundreds of miles. There's a sufficient charging network. So I don't see the energy density being what automotive is optimizing for anymore. Really, I think automotive is going to continue optimizing for cost, and we've seen that over the last few years. That bringing the cost of an EV down is the driver for adoption more than bringing the range up. Whereas in aviation, we're still in that bringing the range up is the requirement. And so this is a divergence in the optimization goals for the technology coming out of automotive. Now, the question would be, even if the goals are different, is the state of the art, the state of knowledge and capability, is that going to improve? As folks go toward lower cost, are we going to also see emergent benefits for aviation? Absolutely. As people do innovation and build new types of electric machines, it's no longer just about what is Tesla using in a roadster. It's about where the larger vehicles, your mid-duty and heavy-duty trucks, what are the power requirements for those vehicles? What are the energy densities required for those? And so it's this expanding fringe of requirements that I think will also drive an alignment in emerging technologies with what aviation is looking for. But the core of a ground car is less likely to directly align with aviation than it did over the last decade, in my opinion.
Are the batteries that you would design around for your hybrid electric conventional takeoff and landing airplane, are they the same ones that you would design around for a VTOL aircraft? And the reason I ask is that an additional difference that I've come to appreciate with batteries for VTOL aircraft is the power output demand on them, especially requiring high power output at the end of the flight as the aircraft transitions back into vertical flight to make its approach at the landing pad. That's a particularly stringent requirement on the battery system. For what you're doing, I don't know, maybe that still exists. Maybe it's the same battery. Maybe you can use the same tech, but how do you think about that?
Yeah, it's a nuance that most of the world, unlike you, Peter, most of the world doesn't catch the nuance between the different types of batteries. The power density versus the energy density needs to be tailored for the application. And what's interesting is you gave two examples. I'll add one more in there around fully electric airplanes. So let's take your eVTOL, which is fully electric, but requires huge amounts of power at a low state of charge at the end of flight, right? So you need a power cell there. Then you have a fully electric airplane, which has a large amount of batteries. And so actually a relatively low C rate, especially if it's conventional takeoff and landing. You're not really draining, and where for those listening, the C rate is the rate of charge or discharge as a proportion of the total pack size. And so that when you have a really large pack, relative to your pack size, you're not discharging that rapidly. And so those can be energy cells because you don't really need that high power C rate. But then you go to a hybrid electric plane. And as I mentioned, our pack is about a third the size of a Tesla pack. These are pretty small, actually. When you come through our hangar, you see this battery is big enough to fly a Caravan, really. And that is because in a hybrid, you use the battery differently than you would in the fully electric. A small battery pack, but you still have pretty high power for takeoff and climb. Again, now you need a higher C rate. You need more of a power cell. And so for each application, you do actually have different requirements for the type of chemistry you might consider, the tailoring of that cell between energy and power. Certainly the life cycle economics of the pack, the degradation over time. You might have great power or great energy, but if you only cycle 400 times, then are you useful? There are all these pieces that go into the details of selecting a battery. And this is the challenge that some companies who are trying to do a one size fits all cell or module for everybody need to hit the high water line or miss the mark on their certain markets. And this is again why I think it's so important to have a more flexible design where, let's say that I need to increase the size of my pack a little bit because I'm not getting exactly what I wanted out of my supply chain, where we can handle that. It's not ideal. We don't desire it. But when you have an approach which is just a little bit more flexible than the pure hard requirement, I think most eVTOL folks, a lot of the ones who've decided to in-house their battery development is because they realize they will not get precisely what they need from anyone else. And they have to tailor it directly.
Given the advantages of the hybrid propulsion to electric, why would the VTOL or the electric plane companies go purely electric versus hybrid? What would be some of their rationale?
Number one is that I hear from them is on the emissions. They want to be able to say they can operate fully zero emissions. Number two is a statement around complexity, the economics of maintenance. And it's an interesting argument, which without being deep into the weeds, it's hard to validate or dispute. All the weeds that I've been in have shown that fully electric still has a way to go before it's economically more viable. But those are usually why I see that there are other ancillary features, like, for example, noise characteristics are important for communities. Oftentimes, the reason communities get upset with aviation is because of the noise. And hybrid electric does not fully eliminate the noise profile to the extent that fully electric does. Fully electric planes, if you've ever flown in one, it's like being in a glider a lot of the time. It's really beautiful. And I think that some people have hung their hats on the sound. And frankly, and to their credit, if you're an eVTOL talking about flying to the city center of Manhattan, you better be thinking about sound.
Yeah, but that's not how people are going to scale in the next several years. At the end of the day, regional air mobility most likely is how vehicles is going to scale in the next, let's face it, 5 to 10 years. And given regional air mobility, given the requirements of the vehicles, I'm guessing that hybrid is going to be the limitations of hybrid are not nearly as impactful as they would be if they're going to city center. And how many city center flights are going to be occurring in the next 5 to 10 years, and especially at scale? So my guess is a lot of people right now listening are saying hybrid's the way to go. Why would they not be saying that, especially as we start to talk about regional air mobility?
Yeah, so it depends on who they are. Let's say that you are an eVTOL developer. We know many. And you've spent the last half a decade investing how many hundreds of millions of dollars into your pure electric design. that is tailored, that every inch of it is optimized specifically for your fully electric operation. You don't have volume, you don't have weight. You would have to redesign your plane in order to integrate a hybrid electric system. And I know this because I've worked with those groups, and we have shown that you can apply a hybrid electric system in, but shoehorning a hybrid into a combustion plane is one thing. That's where we enter the market. Shoehorning a hybrid into something which was designed for a little battery pack is a completely different beast. And I think a lot of these developers have gotten so deep into their fully electric application that they don't have the payload and volume capacity to take on the hybrid electric into their current designs. And so,
But let's say, Kevin, sorry, great answer. But let's talk about the operators who are going to be purchasing these
yeah,
vehicles. Why would they consider a fully, let's step into regional air mobility. Why would they consider a fully electric plane with some of its limitations? Obviously some pluses, but the hybrid, I would assume, is still less noisy, for example, than a traditional combustion
mhm.
engine. Why would they consider a fully electric plane rather than a hybrid for regional air mobility in the next 5 to 10 years? What's their rationale?
I
Put yourself in the position of an operator who has to make that decision.
Yeah. So I would ask, what's the risk? Truly, what's the risk? The risk that I put down an order, even if it's binding, I'm sure there are tons of outs that if this doesn't meet my performance requirements, I don't have to buy it. And probably if I'm putting money down, it's going into an escrow that it can come back to me. Most aren't putting money down for the fully electric type orders that are out there. And so I would look at it and say, I could place an order for a fully electric plane, and if it doesn't pan out, great. If all of the Swiss cheese of good things going right doesn't occur, I probably got a boost to my marketing and brand along the way. And I'm not out any money at the end of the day. I could probably still buy a hybrid down the road. Now, the reality is a lot of these groups are falling behind in our order book. So potentially they won't be as early as they would like. But if magic happens and the performance is what people would love electric to be, then I get the electric plane and everything that I needed. And so I think it's a risk posture that the benefit of placing a signaling order outweighs the risk. And the key for me, as Kevin and with my Ampere hat on, is those folks still place orders for hybrids, right? Like when I talk to folks, they're like, Kevin, this is the first thing that I actually have confidence is going to come to market. I'm going to place an order for this. And what's silly is some of those people still say, and by the way, we don't want to talk publicly about this because our brand is still like fully zero emissions, but we know that this is probably going to come in first. And so we'd like to take part in it.
Kevin, in what way is certifying a hybrid configuration easier or more difficult compared to certifying a battery electric
Yeah,
aircraft?
so the hybrid, one of the reasons it's easier is the safety case. The safety case for our system in the condition where you assume you have an issue with the electric vehicle system, which is really what is the novel parts of the technology. If you're in a hybrid electric condition like ours, you fall back onto a combustion engine and you fly home safely. We have full cruise capacity with our combustion engine. So there's no degradation or risk to that operation if you shut off the electric system in flight. You can't say that for a fully electric or hydrogen, for example, system. That when you have an issue, maybe you have redundancy in the battery packs, but the level of safety that you can take credit for in the hybrid is quite a bit higher. And certifying that is we believe going to be faster and lower complexity and lower cost than going fully electric. The second is around the size and requirements on each of the subcomponents. So whether it's the batteries or the motors, when you look at the reduced consequence of an issue, you can also take a different balance on the probability of certain issues occurring. And so the holistic risk analysis for the safety case, we have a little bit more flexibility. And that means that flexibility translates into the supply chain and our ability to move a bit more quickly in getting those technologies through the certification program.
What's the expected efficiency gain of a hybrid electric conventional aircraft versus the efficiency gain that we are seeing from hybrid electric automobiles? And Is there a difference? And if so, why? And then we can get into efficiency gain that you would see from just like retrofitting an existing airplane versus designing an airplane around hybrid electric, especially for the conventional takeoff and landing aircraft, because going to electric propulsion when you want to do distributed electric propulsion for vertical flight or for electric stall, okay, we get that, right? There's a capability there that's earning its way onto the aircraft. But if you are going for conventional takeoff and landing and you are looking for an efficiency gain, what can we expect to see?
Yeah, so the efficiency of these hybrid systems, and I see hybrid as this gateway technology that as the underlying technology improves directionally toward fully electric, all of it will first get proven out in these hybrid electric conditions. One of the great drivers for adoption of hybrid electric is the fuel efficiency of the systems that we have already demonstrated and have been flying tens of thousands of miles so far in our hybrid systems and demonstrated a 50% fuel burn reduction. During takeoff and climb cycle, we're up closer to 70% fuel burn reduction. So these are actual measurements, right? This is not just an Excel spreadsheet model. This is empirical data and is the kind of benefit that you can get in certain embodiments of hybrid electric systems. So this is pretty significant fuel savings, even when you're looking at the opportunity of hybrid electric on the ground, where call it maybe a 40% fuel savings to 50% fuel savings on the ground. And it's all about the specific architecture of the system. That drives the beneficial economics. Fuel is one of the largest, if not the largest, operating cost for most airlines. And so the fuel burn reduction then drives a positive cycle for the economic viability of new routes and market growth and higher frequencies of service.
What phase of flight are these efficiencies realized the most?
So if you're just looking at a pure percentage basis of fuel savings, takeoff and climb is where you're getting the biggest boost from the electric system in our current architecture. There are lots of different hybrid architectures, and we've got a few of them, but what we're launching into market with is a integrated parallel hybrid architecture where we use the electric system effectively as a boost during the high power phases of flight and the combustion engine as a baseline load of power for the cruise and across the rest of the flight. So you get up to 70% fuel savings during that takeoff and climb cycle. And then it levels off toward about 50% fuel savings during cruise.
I see. What's the state of the art in some of the metrics on the battery side? We talked a little bit about, well, we didn't talk numbers, but gravimetric specific energy density, both at the cell and the pack level, the cycle life that state-of-the-art batteries are achieving, and the battery pack cost itself.
So the batteries, so watt hours per kilogram is the metric that in the industry normally uses to measure the energy density. The target most are aiming for is right around 400 watt hours per kilogram at a pack level. We're not close to that today. When you're looking at the packs today, you're at right around 200 watt hours per kilogram. It really depends on your cooling system and where you draw the dotted line on the battery pack itself and what you include as weight versus don't include as kind of wet versus dry weight for the pack. The cells themselves I remember a few years ago seeing cells that were cresting through the 200s of watt hours per kilogram. And then you get folks who are talking about 300 into the 400 watt hour per kilogram cells. I think I've seen announcements about cells that are even significantly higher than that. Unfortunately, I'm not an expert in the kind of the lab type chemistry that goes into these batteries and the art of understanding where along the long tail of getting from lab into production you are and measuring the number of years remaining is very challenging. And so it's hard to tell what's like state of the art for development of new technologies sounds like it's pretty far ahead in these high watt hours per kilogram. I think the reality is the first battery packs that get adopted into market are going to be at a pack level, maybe even sub 200 watt hours per kilogram when you're looking full scope weight of the system.
And in terms of cycle life and cost?
So cycle life and cost are generally tailored depending on what your application are. So if you've got a more exotic cell, a higher power or energy density, it'll probably have a lower cycle life. I've heard some of our industry peers talking about cycle lives less than 1,000 cycles. I don't see how that makes a whole lot of economic sense when you have to be replacing the batteries so repeatedly. We think that 2,000 to 3,000 cycles, maybe it's 2,000 full depth discharge, but you're looking at, that might give you 4,000 or 5,000 actual flight cycles on a vehicle. That's not unrealistic when you're not working with the most exotic type cells. And from a cost, I think we're pretty conservative, assuming costs are going to be pretty high. And it's hard to tell what'll come out in full production once you actually get to scale. But being at $500 per kilowatt hour, I think would be a great outcome for the industry if we were able to get there. And I wouldn't be surprised if the very first battery packs that came to market were maybe a multiple higher than that. So maybe $1,000 per kilowatt hour, which gets pretty expensive, especially when you're looking at the very large packs for the fully electric vehicles, but is still somewhat manageable with the hybrid electric approach.
I'd like to put some business perspective into the conversation. And if we use, maybe we can get to ultimately the use case that you are pursuing at Ampere, but one of the common near-term use cases for electric aircraft is often thought of on the conventional side as a flight school trainer aircraft. Now, putting aside that the current range restrictions do not enable flight schools to use electric aircraft for the entirety of the curriculum for flight training, but for most missions, it's good enough. What I'm interested in is when you actually go down into the weeds that you've been in, how the business case for an electric, fully battery powered aircraft pencils out when you consider the fact that conventional piston engines are an industry that's been around for decades, benefiting from huge economies of scale, exceptional safety records. It's in the several thousands annual units. A lot of the development and R&D costs have been recovered already. I mean, you're going after a relatively low cost, and I think the engine replacement on this type of application is in the 30, 40, 50, maybe $70,000 per engine. Correct me, guys, if I'm off. But at any rate, you have that on the one hand, and then you have an electric aircraft with a motor that needs to recover the certification cost and development cost, and is one that every 1,000 cycles needs to replace the battery, which can be, I don't know, $80,000 or whatever the cost is. So when you bake all of these different things, does it really become an attractive option?
So this gets back to your first question around what might the industry disagree with me on. And it is this principle that the economics must make sense in order for people to adopt the products. There are a lot of people out there who assume the government subsidies will get us there, or people willing to pay a green premium. And while certain cases that might be true, to hit the scale of adoption that's required, you can't achieve it without really compelling economic benefits for the end user and buyer. So this example that you gave around the training, especially in these smaller airplanes, is a great one. The market makes so much sense. The direct operating cost seems so low when you're only taking into account the industrial power that you're using. It's cents on the dollar for OpEx. But when you look whole scale and you're comparing yourself against a sub $100,000 airplane with relatively low cost of capital, it's probably fully depreciated, and you're comparing that to a $250,000 new build plane that has these unknowns around the cost of batteries over time, or the cost of the infrastructure to charge, the economics are really called into question, especially before you get to full scale. And I think that's rightly should be acknowledged as one of the big risks for adoption. The performance of the systems, especially in training, I think a blended fleet where cross-country flights might have to be in a hybrid or combustion, but fully electric can be done for the few touch and goes here or there, or just familiarization. I think that's completely reasonable to solve the problem. But the economics, especially in smaller airplanes, are pretty challenging. When you look at the economics as you scale to larger planes, it similarly, anywhere that it's not an operator of high frequency becomes challenging, because to earn back the capital cost of the system, you really need high utilization. And you're not generally going against an option which is a premium priced combustion versus a premium priced electric. It's probably a relatively low cost combustion versus a premium priced electric. And I think that'll be a friction point for adoption for those types of applications.
Now, if you were to argue for a fully battery electric aircraft, what is the right initial use case that will generate this flywheel moment where it makes sense and it also is a good path to get to scale, which will have benefits down the road with economies of scale in the supply chain, et cetera, et cetera? What use case gets the industry going, if not flight training?
I think the use case that gets the electrification industry going is using those technologies in full scale applications. So it's taking the exact same batteries, the motors, the power electronics, the certification bases, taking those, and by applying them into the hybrid electric applications, you build the industry base, you build the production volumes, you solve those economic challenges tied in with the supply chain and the certification and the market's readiness to adopt, tying in with the economics of the full scope view. You start to bring those costs down to a point where all of a sudden those same technologies, those same suppliers that are making batteries for the hybrid or making motors for the hybrid, when the economics of scale get to a point, those same suppliers will be the supply base for the fully electric applications, where the opportunities are vast for where you might want to fly a fully electric plane, whether it's short hop island hopping for commercial cargo flights, commercial drones, or for VTOL cargo, or for pilot training. There are a lot of areas where you might want the fully electric. And I think the way to get the industry to scale is by scaling the underlying components rather than scaling the end solution of fully electric. And that's when I talk about hybrid as this gateway technology. I truly believe I'm helping all the electric, maybe even helping some hydrogen out there, like, because we're maturing the industry, we're maturing the supply base, and we're getting up to good economics, full scale marketability of these underlying technologies that ultimately could be packaged in the fully electric. And I think that's how you get there. I've in 8.5 years of every waking and sleeping moment thinking about it, this is the pathway that makes sense to me.
We just had Rob Britton on a couple weeks ago, our last podcast, and he was talking about regional air mobility, and he was saying that it's conceivable that hybrid or electric aircraft will allow us to be able to get to locations that today are less profitable than using a purely combustion engine aircraft. Talk a little bit about that. I'm guessing that hybrid would be the only solution today, although he did mention, I believe, guys, a 30-passenger electric plane as a potential solution in the near future. But talk about the capabilities for hybrid electric for regional air mobility. What's the near-term, long-term solution from your perspective, Kevin?
Yeah, I really enjoyed listening to the episode with Rob and his enthusiasm for regional hybrid electric. You can hear it coming through in the conversation. Love it. And the folks over at Heart, you mentioned a few times, doing some really interesting work in trying to open up the regional space. Also in that episode, he had mentioned that this regional space is kind of eroded over the years. I mean, with deregulation and things having to compete just on the economics really didn't make sense to serve a lot of secondary or tertiary markets. And so the service to those markets has gone away. And that demand still exists. It's just being served by ground transportation, people jumping in their cars instead of flying. If you were able to give an economic alternative, lower cost of operation being the key adoption driver, then people would potentially choose to fly those routes instead of drive those routes. And I think he was spot on with that, and the enthusiasm around regional air mobility. Two areas that I would disagree with the approach, though. One is there's a phenomenal difference between a 19 passenger plane and a 20 passenger plane. While it might look almost the same, it is categorically different. In the literal sense of it is a different category of airplane between Part 23 and Part 33. And the idea that somebody will open up regional air mobility with a Part 25 plane that is something over 20 passengers, I think is faulty logic there. I don't think it's going to be, the Part 25 is not going to be ready for hybrid electric, fully electric, any novel system for quite some time. Now, I want it to be there, and we're certainly helping the industry get there, and there are companies betting their livelihood on it. But this is where I would disagree with the approach, because we believe Part 23 is where it has to start.
Kevin, explain for the audience the nuances of the differences.
So there are two major categories for conventional airplanes. One category, which is under Part 23 of the regulations, governs all planes up to 19 passengers, or the equivalent weight. Part 25 governs all airplanes 20 passengers and above. And so when regulations are updated in the industry, they're updated for one category or the other, eventually both. The smaller aircraft category, Part 23, is already positioned with all of the legislation and regulation in place to adopt novel propulsion technologies. The larger category is not in that state yet. It takes a decade of work to make a significant change to regulation in aviation. And I think we have years ahead of us before the large aircraft is ready to adopt novel propulsion technology from a regulatory standpoint. The technology might be there, but I think the regulations are going to lag in that case. So entering market with Part 23 or airplanes that are up to 19 passengers, I think is the fastest way and frankly, the only way we will see commercial adoption this decade. And that maybe in the next decade, we'll see through the proof points of these Part 23 smaller airplanes, we will see that technology leapfrog up into and enable the conversion of those certification requirements in the larger Part 25 airplanes.
Speaking of regional air mobility, wanted to get your thoughts on whether you think that electric aviation is what catalyzes regional air travel, or is there simply a thickness of the demand that's an issue that needs to be addressed somehow first? We can take a brief look at history prior to the 1978 deregulation. Point to point was the airline network model, and regional travel was subsidized by the government mostly. Post deregulation, we saw the emergence of hub and spoke, and a lot of regional routes were abandoned because they did not make economic sense anymore. So you can look at that to draw the conclusion that, well, actually the demand is there. It's just a matter of making that air travel economic. And so that's an argument for the technology's role in disrupting, again, this segment of the industry. If that's the case, well, first of all, do you think that's the case? And then second of all, do you think that electric aviation is the technology that will make economics appealing, or you need to start layering additional things?
I absolutely think electrification is the pathway to making the economics make sense. And the improved economics drives this elasticity, this growth in the market, where we will see increased frequencies on the existing routes, decreased ticket costs as competition goes up on those, and increased accessibility or flights to fringe airports, either in a hub and spoke extension or a point-to-point model that allows more people to have access to air travel. I think adoption will also be driven in similar economic driver, but through cargo. I think the cargo market will be a rapid adopter of good economics and will be serving, maybe even before the passengers choose to fly to these areas. Same day and next day delivery of packages is a growing expectation for our global economy. And I think that what we'll see is as the economics improve, the cargo operators, so think your FedExes, UPSs, DHLs, and similar around the world, are going to be adopting these both to serve the high-end communities who want their Amazon packages in the next day, but also to open up these billion people markets that don't currently have access to the global economy efficiently, whether that's moving agricultural goods or other products, the economic drivers of increasing accessibility for them. So it's not just about US states and cities. I do actually think on the global scale, these economics open up countries, entire regions of the world that are currently isolated from the global aviation ecosystem and economy. And when you look at that as a driver for scale, it's not about 10% increase in the people who want to fly to Fresno. It's about going from a market of zero to a market of, again, hundreds of millions of people being served for the first time ever, and what that drives. And so I wholeheartedly think that the economics of electrification is what gets us there. It is also on those principles that I think some of the exciting features aren't necessary to get us there. So vertical takeoff and landing, important in some areas, but probably not important for the vast majority. Fully electric and important and beneficial, but not useful if you can't land on that dirt strip in Kenya. Like, you have to have full flexibility. And this is part of the reason why I have such conviction around the regional air mobility being opened up through hybridization, where we don't have any of those infrastructure, range, or operational limitations, but give that great economic benefit.
So, Kevin, let's say we had Part 23 aircraft and we wanted to be able to get more aircraft to cities that are not being well served today. And you're saying Part 23 was the way we'd have to do it today. What's the cost per available seat mile for a conventional aircraft, hybrid, and electric? Assuming the three of them could meet that capability today, what's the relative cost difference between the three?
So the difference in CASM between conventional and hybrid, we're looking, it really depends on exactly how you're operating the plane, right? So it's going to be a range. We're looking at a 20 to 40% savings on your cost per available seat mile. So think, again, depends on how you're flying the plane, going from $1 per available seat mile down to 70 cents, or there's 60 some odd cents per available seat mile. That kind of a transition in certain cases. Electric's harder because right now, when I run the numbers, depends on how you assume battery costs, because batteries are the big replacement cost there. But right now, it does not, in my mind, close economically to go fully electric. Also, it's hard to do the analysis because most of the routes you can't even operate. And then the question comes in on, do I count the grid infrastructure upgrade costs and CapEx and cost of that capital over time in the analysis, or do I not? So it gets a bit muddy. I don't have numbers specifically on the electric in isolation for those reasons.
Have you talked to airlines who today say those routes are not profitable because of the traditional aircraft? Have you talked to them about your operating costs? And are they saying if you can get me a 30 to 35% reduction, that's a route that becomes profitable?
Absolutely. Yeah. The numbers I just talked about are from a very specific model with a very specific airline that I can't mention the names of. But yes, we get into the weeds with our customers and look at their actual operations, their actual frequencies, and how they actually fly the planes, and look at holistic costs, because it's not just about how many miles or hours you fly. About pilot costs, about outstation staffing, it's about infrastructure upgrades. And if you're serious about this, you need to look holistically at every, down to what is the interest rate on the loan that you take out in order to, or the financing that you get in order to buy the system in the first place. Like, there are all the holistic view on the economics, and making sure that is economically positive for our customers is how we get through it.
I really want to underline the holistic approach because I think you're hitting the nail right on the head. There's a lot of enthusiasm about quoting direct operating cost reductions with electrification. But if you look at it in the context of regional air mobility, where you're really competing with cars and rail, and when you are accepting the fact that electric motors are not in their prime time to address this need today, and you start talking about, okay, well, what really do customers care about? Other than price, they care about frequency and the reliability of the schedule. And that means that you have to be able to honor a a service that will be available in all kinds of weather or most weather. So now you start talking about IFR capability, and now you start introducing IFR reserves on top of an already small range budget. And it's only when you look at things holistically like that do you really get a clear perspective on, okay, how really competitive is electric aviation in this particular use case today or over the next couple of years. And I think that there needs to be a little bit more realism.
I agree, because I think that realism is going to be what builds credibility. It's what enables adoption. It's what enables all of these other factors, many of which we haven't even touched on, whether it's the insurance companies or the lessors who have to worry about residual values. The holistic view is the only way you actually get a full ecosystem to buy in. And I just recently had a deep dive with one of our major customers on IFR, speed, and flight into known icing conditions, because these are the realities of their operation. And we need to know, hey, if we choose to fly 5 knots faster or 5 knots slower, what are the repercussions? If we are flying, we guaranteeing IFR, or if what happens if you're not flight into known icing conditions? You're hardly useful, because it's not just Alaska where you have to deal with icing, right? It is everywhere that you have to be confident in your aircraft's ability to operate. Otherwise, these mission critical operations have to ground the plane. And if you ground a plane in one of these operations, it destroys a whole network. It has a residual ripple effect through the operations until recovered. So it's important to have these capabilities.
So here's a thought, Kevin. What if, after all is said and done, the 30, 40, 50% improvement really becomes something more like 10%? I'm talking hypothetically here, right? At what point does it make more sense to incrementally improve the efficiency of a turboprop or a conventional aircraft that is certified, well-known, all of those things, and perhaps kickstart the electrification supply chain on the unmanned side of things?
It makes a lot of sense to find wherever you can build the efficiencies into the operation. From the airframe design, there's some folks out there who, with traditional engines, are looking at cutting 30 to 50% of the fuel burn out of your 737 class planes by bringing blended wing body type airplanes to market. So there are ways that you can, by creating a new aircraft, even if you're not changing propulsion, you can get some meaningful efficiency gains as well. At the end of the day, when you achieve fewer economic benefits, it reduces the addressable market for the technology. So, or inverting that, for every percent cost that I save, it opens up more and more market opportunity. So there's a old story in the industry about a major airline that removed a few pages from their in-flight brochure to save a few pounds because that mattered, right? And these are fractions of a percent saving. So in your example of saving 10%, still transformative for many operations. Now, is it going to be as transformative as saving 40? Nowhere close. Will it still be meaningful? Only if it's economically compelling. And so this is where you look at the conversion. So maybe somebody struggles to retrofit their plane, but if you're buying a brand new plane and you get to choose between a CapEx neutral across the two, the combustion or a hybrid, and that hybrid saves 10% on your OpEx, you might still go with the hybrid system because economically that still makes sense. So this could be a factor that delays adoption if the economics don't work out. From an unmanned standpoint, we're already seeing from drones, eVTOL, or like the Department of Defense type applications, some fully electric, or places where the economics don't matter as much, where they're willing to pay a premium for the mission capability. Those are certainly additional early adopter areas where I think the industry is likely to get a boost, regardless of the fuel savings, a boost in market applicability because of the performance characteristics of these new vehicle types.
Is the drone propulsion supply chain overlapping into the propulsion supply chain that you deal with?
Absolutely. So a year and a half ago, we acquired a company's assets the company was named Talon. And Talon was developing effectively a cargo lift drone and various types of payloads that it could carry. Our propulsion systems fit straight into that cargo drone, straight into traditional conventional takeoff and landing drones or eVTOL for a whole variety of applications. Ampere's focus is, again, the disagreement place number one. Propulsion is where you begin. And I want to put propulsion across everything. And yeah, so the same engine types, I mean, there are flavors and variations of engines, but the major families are applicable across the industry, whether it's manned or unmanned.
Kevin, tell us a little bit about Ampere. How do you make money today? How do you make money in 5 years and 10 years? What's your special sweet spot?
So Ampere is focused on the electrification of aviation, focused on propulsion, specifically hybrid electric propulsion, upgrading existing aircraft types as an entry point into market, and using that as a gateway to transition the industry toward lower carbon and better economics.
Give examples of the type of aircraft that you're converting. I saw a Skymaster as one.
So back in 2019, we flew our very first aircraft type, which was a upgraded Cessna Skymaster, push-pull configuration. We call that an independent parallel hybrid architecture where you have one combustion engine, one fully electric. We've also flown the Cessna Grand Caravan, which is with an integrated parallel hybrid architecture that uses a mechanically coupled electric and combustion set of engines to be a hybrid electric aircraft. That same engine that goes into the Caravan is what we just finished our CDR on the King Air for integrating there. We've got the Twin Otter, is a 19-passenger plane in the same category, and there are thousands of planes in market that use this category of engine. So this is our half megawatt class system. We also have a quarter megawatt class system, which is used as either a genset or propulsion system for general aviation, drones, and eVTOLs. Now, as a company where our focus is around the certification of that launch product and the Caravan, the market that adopts that is both passenger carrying and cargo carrying for the commercial industry. But then also we've got a number of contracts with the Department of Defense, NASA, and the Department of Energy. So our money today, our revenue, which is really just offsetting NRE costs or non-recurring engineering costs, we've brought in about $25 million of government contracts through these government customers for the development of our propulsion system and the application of that system.
If you're making $500 million in 5 years, who are your primary customers?
So when we scale commercial revenue, this comes from the regional aviation market. These are folks who are currently buying turboprop engines and would, instead of overhauling their engine or buying a new engine, would be buying one of Ampere's hybrid electric amp drives. These amp drives are the ones which save 50% fuel burn, and we believe will save on maintenance cost as well. So it'll be good economics for people to switch over to our systems rather than run on their traditional combustion system. And this is where we see the earliest adoption for technology. So begins as retrofits of the existing fleet of turboprops, but then quickly moves into partnering with OEMs, the aircraft manufacturers, for when they build a new airplane, giving it a hybrid option. The next phase is, of course, working on clean sheet design planes with OEMs who are optimizing planes, new designs around the novel propulsion.
Tell us a little bit about you have a great history of being an innovator and entrepreneur. Give us some lesson learned to our innovators who are listening today.
Yeah, so it's been 8.5 years at Ampere. The number one and biggest recommendation I can give is choose something that you deeply love and that you think you can actually achieve. The days get challenging over the course of years as an entrepreneur. It is not easy. It is oftentimes not even fun. But when you know that you're doing the right thing, when you're tackling the most meaningful, challenging, visible problems that you possibly can, it gives the motivation, not just for you as an individual, the innovator, but truly these are things done by teams. And when you have meaningful work and you're thoughtful about it, it enables you to pull together teams of really great people to go do these audacious things. I think the importance of setting tangible and tractable goals that you can actually achieve in the near term is very important. It's not just about moonshots, it's about the steps on how to get there. And ultimately, it's about building long-standing relationships and not looking for what do I get now or being short-sighted in them, because truly the world is built by people and supported by relationships that are built over years or decades. And so being a good actor in the industry is so important.
Kevin, you've acquired companies. You were almost acquired yourself. What advice would you have for people who might be going through a similar process?
Yeah, so always be open to opportunity and thoughtfully assess it. In 2019, 2020, and 2021, the opportunity to go public via SPAC was pretty exciting, and there was a whole lot of money on the table, both from company valuations and from operating budgets. But you also have to be willing to change course when it's clear that the course you're on is not the right one, which we did in early 2022. Ampere pulled out of a deal to go public because we realized that it was the higher risk path and was not worth continuing down that path of going public and getting acquired. These are hard decisions that you need clarity, you need good advisors and mentors to support you on. And ultimately, you need to set the ego aside a lot of times and go on good first principles when making your decisions.
Kevin, thanks a lot. What a great conversation. Thanks for your time.
Thank you so much.
All right, that's a wrap for today. Thank you for listening to the Vertical Space podcast. Reach out if there are topics that you would like us to discuss, and goodbye until the next episode. Unless mentioned, this podcast is in no way endorsing or promoting any person and/or company mentioned, and all opinions within the podcast are solely that of the presenters. The Vertical Space makes no guarantees, warranty, or representation of any information given in this podcast. Any information given is for informational purposes and should be used at your own risk. This podcast is for general, educational, and entertainment purposes only.